Now that we've made friends with the idea that an infinite sum could indeed be finite, the natural question to ask certainly is, well, when does an infinite series converge? And the answer to that is a little bit disappointing because at best we can say it depends. There are various tests that imply that a series converges. There are also tests that imply that a series diverges, such as the limit test. And if one of these tests works and decides the series one way or the other, that's okay. But there also are situations in which no test really works out, and then we may have to even invent a new convergence test potentially. In this presentation, we're going to talk about some fundamental convergence tests for series, specifically geared towards getting to the ratio test as fast as possible, because the ratio test is the test that is making our presentation of power series and most of the regular computations on power series possible. So let's take a look. As an introduction, again, a reminder, there is no single criterion that decides whether a given series converges or diverges. There is no single criterion that does it for all series. So each of the convergence tests that we're going to look at will be applicable in some but not all situations, and that is then certainly also why series teach mathematical reasoning, even at this early stage of calculus when most of our focus is on modeling, visualization, and computation, because what we have here is we have a bunch of implications where we have A, B, C, and D implies convergence, and then E, F, and G implies divergence, and if we can use one of those implications, great, but if we can't use any of those implications, then we are still left to try to figure out something else. A common mistake, and I've already said that once in the previous presentation, but just to reiterate, just because the terms converge to zero does not mean that the series converges too. So don't do that, don't use that false conclusion. Remember that the harmonic series sum n equals 1 to infinity is in fact infinite. It has an infinite sum, and that means it is not convergent. Yeah, there was something else I was just about to say, and now I don't recall what that is, so we just go ahead and move on. Theorem, our first test that we're going to look at, is the comparison test. And the comparison test says that if we have two infinite series, sum n equals 1 to infinity an, and sum n equals 1 to infinity bn, so that both the series have non-negative terms, 0 is less than or equal than an is less than or equal than bn, so b is the bigger series, if you will. If then the series of the sum of the bn's converges, then the sum of the an's converges too. And equivalently, the contrapositive states that if they're both infinite series, so that 0 smaller equal an smaller equal bn for all n, and the sum of the an diverges, then the sum of the bn diverges too. So here's where we also have a little bit of logic, which is sum bn converges implies sum of the an converges. The contrapositive would be the sum of the an doesn't converge implies that the sum of the bn doesn't converge, and that is exactly what we have here. Sum of the an's diverging means that the sum of the bn's diverge. So that means we only have to prove one of these, technically two statements here, and we're going to prove this one. So for the comparison test, the sketch is actually meant literally. Let's look at the sequence of the bn's, which will be the blue dots here. That is a sequence like that. And what we know is that the bn's all exceed the an's, which will be the black dots. And we know that an and bn are both greater or equal than 0. So we have this relation that bn greater or equal an, and that is greater or equal than 0. And that works, of course, then at every stage. So the two sequences line up like this. If we're now interested in the series, remember that the series is the sum of these rectangles that we erect with width 1 and height being the value at 1, the value at 2, the value at 3, and so on. So the sum of the bn's, which is the blue and red area that is aggregated from all these rectangles here, because all the b-ends are greater or equal than the a-ends, the sum of the b-ends will include the sum of the a-ends, so it must be exceeding the sum of the a-ends because the black area, every black rectangle, is actually contained in a corresponding blue and red rectangle, and so the area that represents the sum of the a-ends is smaller or equal to the sum of the b-ends, which is represented by this blue and red area here. And we cannot squeeze an infinite area into a finite area, which means if the sum of the b-ends converge, if the blue and red area is indeed finite, then the black area must be finite also. Again, in a formal proof, you would actually have to explicitly invoke the monotonic sequence theorem. We don't do that here, we just stay at a more intuitive level. Either way, this is the end of the sketch for that proof. Okay, so to see an example how the comparison test works, let's take a look at the series sum n equals 1 to infinity, 5n cubed minus 12n squared divided by 4n to the 6 plus 12, and we want to determine if the series converges or diverges. Now, one of the things we know about the comparison test is that it applies to series with positive or non-negative terms, and we can see in this series that for n equals 1 we get 5 minus 12, which is negative 7. For n equals 2, the computation is a little bit harder, but we get 5 times 8 minus 12 times 4, which is 40 minus 48, which is negative 8. And only when n equals 3, we get 5 times 27 minus 12 times 9, which is 135 minus 108, which is positive. So only once we're at n equals 3 and higher will we have positive terms here. However, that is something that for the comparison test actually does not matter. It is not a problem that the first two terms are negative, and that is because for convergence of the series, we're interested in what happens for large values of n, and that means n equals 1 and n equals 2 can always be outliers if necessary. Alternatively, we could also simply say that we're going to consider the series that only consists of the positive terms, with the first two terms split off, and then apply the comparison test to it, which is completely clean because all the terms are positive. And we can then, after we have decided whether it converges or diverges, if it converges, we can add the first two terms at the end. So first, quick mental note on the comparison test: if you have a couple of negative terms at the beginning, as long as you don't have infinitely many negative terms, that would not be a problem. Now, in terms of applying the comparison test, there are two major steps that need to be taken. First of all, we need to figure out what to apply these terms to, and then we have to verify that the right inequality works. In terms of figuring out what to compare these terms to, well, if we drop all the lower order terms here, we realize that this fraction sort of looks like 5n cubed divided by 4n to the 6th, which is about 5 over 4n cubed. And that literally is how you want to look at this stuff, because as n goes to infinity, the lower order terms really will be negligible in comparison to the higher order terms. Okay, so that means that we would want to compare the series to 5 over n cubed, and we know from p series that with a p series with p equals 3 converges, so that means we need to verify that the terms of the series are smaller than 5 over 4n cubed. Now, there are many ways to do this, and you probably want to practice working with inequalities a lot more than just this one example here. However, in this presentation, we want to get very quickly to the ratio test, so we're going to stay with just one example. And well, so after the first step is done, after you know what term you have and what you want to compare this term to, and you have the direction of the inequality, which is that if you want to compare to something that converges, then your inequality must be that your series that you're testing has terms that are smaller than what you are comparing to. Well, then you have to somehow show that the inequality works. And there are several ways to do that. One of them that I think early on is legit is to simply simplify this inequality until you have something that is correct by inspection, as long as we work out our steps correctly. So here, for example, this inequality, we could multiply with the denominator on the left side, and that denominator is positive, which means the inequality is not affected. And so the first line is equivalent to checking whether 5n cubed minus 12n squared is smaller than 5 over 4n to the third times 4n to the 6 plus 12. And well, now we can just multiply out the right-hand side. So this is equivalent to checking whether 5n cubed minus 12n squared is smaller than 5 over 4n cubed times 4n to the 6th, which is 5n cubed, plus 12 times 5 over 4n cubed. Well, 12 over 4 is 3, times 5 is 15. So we get the 15 over n cubed here, and this inequality by inspection is correct, because if you have a number and subtract something from it, then that certainly is smaller than when you have a number and add something to that number. Now, the logical presentation, the logical derivation of this inequality actually would have to go from the bottom to the top, because logically we have to start with something that is correct, and from that conclude that this is correct and then this is correct. However, because all the steps that we have here are reversible, we will forego these technicalities. Working with inequalities is a huge topic that you probably want to spend more time with. However, in this presentation, that is not one of the main goals. We want to push towards the ratio test. So to conclude this example, we would say that we can conclude because the terms of the series are bounded by 5 over 4n cubed, and because the sum n equals 1 to infinity 5 over 4n cubed, which is just 5 quarters, times the sum n equals 1 to infinity 1 over n cubed, which is a p-series that converges. So because that upper bound converges, the series sum n equals 1 to infinity 5n cubed minus 12n squared divided by 4n to the 6 plus 12, that series converges, and that's where we leave it at. Okay. With that, we're going to talk about absolute convergence. And the big note that we have here is that the comparison test focuses on series with non-negative terms. Well, this kind of suppressing negative signs is actually a very common step, and it goes hand in hand with the following definition. A series, sum n equals 1 to infinity an, is called absolutely convergent if and only if the series sum n equals 1 to infinity an absolute value of the absolute values of its terms converges. The language basically indicates that if a series converges absolutely, then the series should converge, but that is something that we have to prove. Just because the language is suggestive does not mean that the implication holds. The proof isn't too bad, because the key to the proof is something that somebody has thought about for a long time. If I take an plus an absolute value, then I no longer have negative numbers, because if an is negative, then this sum is 0, and if an is positive, then this sum is 2an absolute value, and so that means that an plus an absolute value is between 0 and 2an absolute value. And this is something where we can use the comparison test for, because we know the sum of the an converges absolutely, which means that the sum of the an absolute value converges, which means that the sum of 2 times an absolute value converges also. And that means the comparison test implies that the sum of the an plus an absolute value converges, because they are greater or equal than 0 and less than or equal than this convergence series that we know. And that means now we can use algebra and realize that the sum n equals 1 to infinity an plus an absolute value minus the sum of the an absolute values, that's the sum of the an plus an absolute value minus an absolute value, which is the sum of the an, which therefore is a convergent series. Okay, as an example, the series sum n equals 1 to infinity negative 1 to the n divided by n cubed converges absolutely, and that is because the sum of the absolute values is just the sum n equals 1 to infinity 1 over n cubed, which converges by the p-series test. So that again shows that absolute convergence implies convergence. Now, it would be very nice if the other direction were true also. However, that is not the case, which means that there will be series for which we cannot suppress the negative signs. And the standard example is what is called the alternating harmonic series, the series sum n equals 1 to infinity, negative 1 to the n plus 1 divided by n. What we're going to show in this example is that this series converges, but not absolutely. And, well, because the absolute value of negative 1 to the n plus 1 divided by n is just 1 over n, and because the harmonic series diverges, remember that was the warning at the beginning of this presentation, that's the one that you always want to keep in the back of your mind. Because the harmonic series diverges, the series sum n equals 1 to infinity, negative 1 to the n plus 1 divided by n does not converge absolutely. For convergence, that takes a little bit to work out. So let's look at convergence from the point of view that we pair up consecutive terms in the partial sums. Then a partial sum that goes from n equals 1 to an even ending index 2n of these guys will be the sum n equals 1 to n of 1 over 2n minus 1 minus 1 over 2n. So this is a summation that starts with n equals 1 here being 1 over 2 times 1 minus 1, so 1 over 1, just like this one starts here with 1, minus 1 over 2, which would be the term for n equals 2 here, with a negative sign. And it continues like that with alternating negative signs up to the term 1 over 2 times, negative 1 over 2 times capital N, which is exactly what we would get here if we plug in 2 times capital N, because negative 1 to the 2n plus 1 is negative 1 times 1 over 2 times capital N. So these two sums really cover the same terms, but now here we can do some algebra. And if I find a common denominator, I get 2n minus 1 divided by 2n minus 1 times 2n. Well, the 2n minus 2n goes away, and we just end up with 1 over 2n minus 1 times 2n. And we realize that that is less than or equal than the sum n equals 1 to capital N of 1 over 4n squared. I've just dropped the minus 1 in the denominator, which makes the whole fraction larger. And that is less than or equal than the sum n equals 1 to infinity 1 over n squared, which converges by p-series test. And so the sequence of even-numbered partial sums is increasing and bounding, which means it converges increasing and bounded. And so that means it converges by the monotonic sequence theorem, if you will. And similarly, we can actually show that the sequence of odd-numbered partial sums is decreasing and bounded, where you just go from n equals 1 to 2n plus 1. And if that is decreasing and bounded also, then that means that that sequence converges also. And the difference between consecutive even and odd-numbered partial sums is just a 1 over n that is being added or subtracted, and that means they must have the same limit because their difference goes to 0, and that means that limit will be the sum of the series. This kind of alternating series approach is something that we're going to talk about some more when we discuss the alternating series test. However, that is a separate test that isn't crucial to talk about power series, and as I said, I wanted us to get as quickly as possible to the ratio test, where we also need absolute convergence because that is something that the ratio test talks about, and so it made sense to explore a little bit as to how convergence and absolute convergence are related to each other. So now the ratio test. The ratio test says that if you've got a series with non-zero terms, so an not equal to 0 for all n, and if you then consider the limit n going to infinity of an plus 1 divided by an absolute value of the absolute values of quotients of consecutive terms, then you have the following. If this limit of these quotients is smaller than 1, then the sum converges absolutely, and in particular that means it converges. If the limit is greater than 1, then the sum diverges, and if the limit is equal to 1, then the series might converge or diverge, and we also say that the ratio test failed in this case. So again, this is something where we have a test that says, all right, if one thing happens, we've got convergence. If another thing happens, we have divergence. But there is still a third case where we don't quite know what to say. And that third case we can actually discuss fairly quickly. If you look at the harmonic series, as well as any of the p-series, the limit of the quotients of consecutive terms for all these series is 1. And some p-series converge and some p-series diverge. So the most important part for the proof is to prove parts 1 and parts 2, the case distinction between whether the limit of the quotients is smaller than 1 or greater than 1. And that then, let's see, these limits are also then one of the reasons why it is hard to work with series. Let me see if I can grab this somewhere. Yeah, here. Because now not only do we have the sequence of the terms as well as the sequence of the partial sums, but now we also have the sequence of these quotients. That is a quantity that we have to think about, and the case distinction is different, right? If the terms don't go to 0, the series is divergent, where here we have something where we argue around a limit of 1. So we need to make sure that we remember all these details. In terms of proving the ratio test, it's actually not that bad. For part 1, we assume that the limit is smaller than 1, and we take the average between that limit and 1. So we take q being 1/2 being the limit of the quotient, 1/2 times the limit of the quotients plus 1. That's smaller than 1. And for sufficiently large n, remember limits act when things get large. For sufficiently large n, we have that 0 is less than or equal than a, n is less than or equal than some number m times q to the n for m greater than 0. And that's because an plus 1 divided by an is smaller than q, and that means an plus 1 is smaller than q times an, which means that it's smaller than q squared an minus 1, and so on and so on. And so recursively you can ultimately derive an inequality like this one. And therefore, by the comparison test, the series converges absolutely, and that's already it for the first part of the ratio test. For part 2, let's note that if the limit is greater than 1, then for large n we have that an plus 1 absolute value is greater than an absolute value, and so for some large enough n, we have that an is c greater than 0, and that means for all the n's that come beyond that, we have that an is greater than c, and that means the terms of the series don't converge to 0, and the series diverges by the limit test. Okay, this kind of reasoning is certainly something that is also on the border of going to an advanced calculus class where proofs take center stage. Check with your teacher how much of the proofs will be required of you. We're now going to look at how the ratio test acts. We'll have two examples. The first one is to determine if the series sum n equals 0 to infinity, -1 to the n times n divided by 2 to the n converges. So we take the limit of the quotients of consecutive terms, which are -1 to the n plus 1 times n plus 1 divided by 2 to the n plus 1 divided by -1 to the n times n divided by 2 to the n, right? This term here at n and at n plus 1. All right. So if we simplify the fraction here, multiply with the reciprocal of the denominator, we get the limit of -1 to the n plus 1 times n plus 1 from here, times 2 to the n, which is the denominator of the denominator, divided by 2 to the n plus 1 from here, times -1 to the n times n, which is the numerator of the denominator. The negative signs actually I could have cancelled already because everything is inside an absolute value, so the negative signs don't do anything. Then we can cancel the 2 to the n against the 2 to the n plus 1, leaving us with a limit of n plus 1 over n times 1/2. And as n goes to infinity, n plus 1 over n goes to 1, so the limit is 1/2. That is smaller than 1, and that means this series converges by the ratio test. And that's the end for this example. So after we actually have internalized the ratio test, applying it actually isn't that bad, and that also is the case when we have a more complicated series, such as the series n equals 0 to infinity n factorial divided by 8 to the n. Again, we set up the limit as n goes to infinity of the n plus first term, which is n plus 1 factorial divided by 8 to the n plus 1. And we divide that by the nth term, which is n factorial divided by 8 to the n. We simplify. This is the limit as n goes to infinity of n plus 1 factorial from the numerator times 8 to the n, which is the denominator of the denominator, divided by 8 to the n plus 1, which is the denominator of the numerator, times n factorial right here. Now the cancellation of 8 to the n versus 8 to the n plus 1 giving us 1/8, that's not a problem. Something that can trip people up, I've seen it happen, is how do you cancel n plus 1 factorial and n factorial? Well, n plus 1 factorial is the product of the first n plus 1 integers. So that's 1 times 2 times 3 times all the way to n times n plus 1. N factorial is 1 times 2 times 3 all the way to n. If you cancel all that, the only thing that remains is an n plus 1 in the numerator. So this is the limit as n goes to infinity of n plus 1 over 8, which is infinity, which is most certainly greater than 1. And so that means the series diverges by the ratio test. Quick note, in Taylor's series we will have an n factorial in the denominator. And if you had an n factorial in the denominator, then this computation would work with the reciprocal here essentially and would end up with a limit of 0, which would indicate convergence. And so that means unless the numerator behaves really badly, and that can happen, but unless the numerator behaves really badly, the Taylor series actually will converge, and we will see that as we talk about power series, which in the order in which I have lined this out for my text at least will be the next presentation. If you are first interested in just convergence tests for series in general, if you want to get all of those out of the way, you would skip the power series and go to further convergence tests. I leave that up to the instructional design of your course or your choice. Right now, what you want to do is you want to test some series for convergence and divergence, and you want to use the comparison test and the ratio test for that. Have fun.